Of course, today is going to be a tutorial session. We'll try to allow you guys to solve some problems. So we will go one by one, inshallah. So let's start with the first one. You have 100 kilogram per hour of a mixture of solute A. So you have this mixture feed. You have 100 kilogram per hour. So you have the solute is A and the carrier is B. So binary mixture is going. Contains 50% of A and 50% of B. So this is 50-50. Is to be extracted using a solvent stream. So we're going to mix it with the solvent. Okay, call it S, for example. And this stream contains 20% A. So it's not 100%. So it is, let's call it solvent S is 80%. And the solute is 20%. In a single stage, so this is only one stage. And then you're going to, of course, have this raffinate and extract using the solubility data in this table, this solubility data. Determine the maximum and minimum amount of solvent required. Okay, so what is the maximum solvent and what is the minimum solvent requirement? And what would be the corresponding extract and raffinate composition? So the maximum condition, what would be the XE and XR? So this is XE and XR here. And at this condition, what would be the extract and raffinate conditions or compositions? Okay. So you basically have to draw the lines here. Now you know this is your solute and this is your carrier and this is your solvent here. See. On this, the carrier B, and this is the solute here. Okay, so I give you maybe probably less 10 minutes, and if you finish it, just let me know. Okay, so you have to draw the. Let me give you some idea. So you have to draw the two lines. This is your percentage of the solvent, percentage of C, and this is percentage of A, which is the solvent, the solute. So you have to draw this line, and you have to draw another line, and you have to locate your position, the feed point, and you have to locate your solvent point, and you contact them together. And now you have to see what is the maximum and minimum, what is the minimum and maximum amount of solvent that you have to use. Okay. So hopefully you have the graph paper that you can start solving the problem. Okay. I give you 10 minutes, inshallah, I'll get back to you. We will see the solution together, inshallah. Okay, guys, have you been able to solve it or? So okay, now so as you see here, we have to draw the equilibrium line. We need it, and we use this one, the extract and the raffinate composition of the solute, because this is the solute, and this is the extract with solute here, with percent of solute in the extract, which is this one, and this one is going to be this value. So you will end up with this straight line. You will need this one in the next slide here. So as we said, we have to determine the solvent. We draw the line of the equilibrium, the two lines. Now we have to specify, and we know that the problem statement says we have feed contains 50% A and 50% B, and the solvent basically contains solvent 80%, and solvent is 80%, and the solute is 20%. So now from this diagram, you can see easily your feed should be 50-50. So this is your feed, and your solvent contains, it's not 100%, it's not here, it contains 20% there. So we go up 20% and go to the right until we reach this point. So this is your solvent here. Once you decide or locate your points, now you just connect them. This is the line that we have to draw. Now from this line we can determine the maximum and the minimum. Now the maximum should be this value, and this is the limitation. This is where exactly you have to be. So you have to be in this region to be able to do any separation, and therefore this will represent the maximum solvent, and this will represent the minimum solvent. Okay, now how are we going to be able to use this one? So we know this one represents the endpoint, of course. So now this is the tie line. How we determine the tie line? In fact, we go to the diagram here. When I have this one is the extract, because this we are in the solvent here. This is your solvent, or this is the extract layer. This one is the extract layer. And this one is representing the raffinate layer. So now I'll have to do, I go to the point here, and at this point I have around 47 or something. Okay, now I go to this one, the extract layer, the raffinate. So it is going to be almost 50%. So this one should be 50%, and that's exactly what you see here, 47.5. This is the M point and represents the minimum condition, and this one is going to represent the maximum point. Now a maximum point, I have to go to this one, and this one is around 28 or something. So I go to the 28 here, and I go down here. It's going to be 20, maybe 3 or something like this, or maybe 27. Okay. Now once I know xm, I go back to the equation we have all the time, mass balance equation. We say F plus S is equal to M. Okay, and we know xm is basically the feed composition, which is 50%, so it's going to be 50% multiplied by the flow rate of the feed, and the flow rate is given as 100, plus the 20% of the solute in the solvent, and now divided by S plus 100. Now, when you are substitute X minimum, then the solvent here, flow rate, you obtain from this equation will represent the S minimum. When you substitute Xm to be this number, that solvent you're going to calculate from this equation will be representing the maximum solvent. So basically what we can say X now we can write this equation again and base it on the minimum. So you're going to say 0.475 is going to be 50 here, plus 0.2 is minimum divided by S minimum plus 100. When I substitute with 0.28, I still have to feed 100. I still have the same concentration of solute in the solvent, but now S will represent X maximum over X maximum plus 100. So as you see here, when we change this number, we change the value we obtain. Is this clear, guys? Okay, so let's go move on to the other problem here. You have 3 kilograms per second of a feed that contains 60% of A and 40% of B, solute and the carrier, the same equilibrium data, and is to be extracted by pure solvent C, pure solvent, in cross current extractor of 3 stages. So you're going to have 3 stages. Stage 1, stage 2, stage 3. And in each stage, you're going to use different amount solvent, pure. So here, 100% solvent and 100%, and here also 100% solvent. So if I want to label these, I will say this is my feed 1, and this is going to be R1, and this is going to be R2, and this is going to be R3, and this is going to be E1, and this is going to be E2, and this is going to be E3. Extract, extract, extract. And this could be solvent 1, solvent 2, solvent 3 if they are different in values. The flow rate of solvent is so this one is 3 kilograms per second the feed, and I know X here feed is equal to 0.6 here. The flow rate of the solvent is being 3 kilograms per second to each stage. So here this is the same. So 3 kilograms per second, 3 kilograms per second, 3 kilograms per second. What are the compositions and flow rates of the raffinate and extract leaving the third stage? So what would be this value R? And what would be XR3 also? And what would be the value of E3, and what would be the value of EX? So as you see here, we have to treat this one as single stage, and we have to repeat the calculations based on the same equilibrium data. But we have each time we have different feed. So we have XR1 here, XR2 here. So now we start with the first stage. We solve it. We obtain XR1, R1, and E1 and XE1 and XE2 here, okay, and then we take this one as a feed to the another stage, and we solve it individually separately. We will get XM2, of course. Again, we're going to, but now there's one thing you have to understand and you have to remember. Now this feed is not at equilibrium in instant, so it's not going to be sitting on the equilibrium line. But for this one, XR1 and XR2, because they are coming out of in equilibrium conditions, they were together with the extract layer, so they are at equilibrium with the XR XR1 and XE1 are at equilibrium, and therefore XR1 should be on that line. So you're basically going to have something like this one. Once you draw the data, okay, so now your solvent is pure, so this is your solvent here. For all stages, you start with the first stage, F1, okay, and then you draw the line. You obtain X, first X, and this will be representing XM1, okay, and you try to do this trial and error to obtain the tie line that is going to be passing to the same XM here, and that will represent E1 and XE1, and this will represent XR1 and R1. Now this XR1 is going to be fed to the second stage, so I have to connect it with this line, and then I have to calculate XM2, and that will be XM2 here. XM2, I have to do trial and error until I get another tie line that is going to pass through this endpoint, and this one will be XR2, and I connect it to this one, and I find out the the last XM3, and therefore this one will be XE2 and XE2, and this one, once I draw this data and I draw the tie line, this will be E3 and XE3. Okay, so try to do it at least one stage or two. Try with one stage. But now the feed is, now you have to keep in mind the equations that you're going to use. XM for any stage is going to be the feed of that stage plus the X of the feed of the solute plus multiplied by the feed and plus the composition of the solute in the solvent multiplied by solvent over S plus feed. Now here, as you see, the solvent is pure, so here this one is going to be 0. It's not like the previous problem. So now I have, when you're going to substitute XM1, you're going to have XF and F. But when you're going to calculate XM2, this one here, you'll have to substitute here, instead of XF multiplied by F, you have to substitute with XR. So here we can say XM2 will be XR1 multiplied by R1 plus X solvent multiplied by solvent over R1 plus S solvent. And XM3 is going to be related to XR2 PR2. So an X will be XR2 multiplied by R2 plus XS multiplied by S divided by R2 plus S. Okay, I give you 10 minutes, probably it should be enough, and see how you deal with it. At least you do one stage, okay? Okay, guys, we'll move on and just show the solution. So it's basically, as I said here, uh, hmm, yeah, that's exactly right. So this is, sorry, so yeah, based on the flow rate of this one, which is zero point 0.3, I guess, zero point 0.6 here. So you have to, this is your feed one, and it will be mixed with the solvent here. So this is stage one, and then if you do the, as we said here, you have 60% with feed, which is 3 kilogram per second, and this is 0%, so x is equal 0, and it's 3 kilogram per second. You can get xm. This is xm first one, so this is xm1, and then once you do the trial and error to obtain the, this will be xr1, and this one will be used as a feed, so you connect it with this one. So this is the other line. This will represent stage 2, and so on. And you can calculate using the same equation. You can calculate xm m2, and then again do the same thing. You can get xm3. Very straightforward. But as you see here, xr1 and xr2 are at the same line here because they are coming from, this is xr1 and r1, and this is r2. So you see r2 are at equilibrium with e2, and R1 is at equilibrium with E1. So they are at this line. They are at the extract line, the raffinate line. Okay, good. So now let's, I'm not sure if we have enough time, but yes, we still have time. Now we have now 1,000 kilogram per hour of 45% acetone in water solution. And is, so this feed contains acetone and water. Binary system is to be extracted in a continuous counter current. So we're going to use counter current stages here, as you remember last time when we explained these ones. Uh, with pure, so your solvent is pure, trichloroethane to obtain a raffinate containing, so XR N is equal to 0.1. Using the following equilibrium data, determine with an equilateral triangle diagram the minimum flow rate of the solvent, the number of stages required, and the يكون when the solvent rate is equal to 1.5 times the minimum, is similar to what we did last time in the example, and see the flow rate and composition of each stream leaving each stage. So now here we have it's a different way of representing the tie lines. So you have only 3 points. These are the tie lines that you're going to use to obtain the rest of the equation. So first of all, we have to uh, draw the equilibrium line, and this is going to be the extract, we call it XE here, weight percent of acetone, which is the solute in the extract phase, and here is going to represent the weight percent of acetone in the raffinate phase. So we use this one. So we have 3 points, and these 3 points we connect them with the line that is going to be used to obtain the relationship between the extract and raffinate composition. So now I will use this diagram to draw the raffinate line, and this is going to be between acetone. This is the acetone, this is going to be your Y, and this is going to be your X here, trichloroethane. And I will use this extract layer. So this one is representing the raffinate layer. And the other line here is going to be drawn using the extract layer. Okay. Now I know the composition of the feed is basically 45% acetone. So 45 is going to be somewhere here. Okay. So now what we do, we try to obtain the minimum. So in the counter current, we have something called delta R here. So we have to determine, first of all, delta R minimum. Now, delta minimum, as we explained before, it is something that we're going to do. I know this is the solvent and this is your feed, and this is your XR, it's 10% here. Okay, so now you try to draw a line this way. This is your feed, for example. So you're going to try with different trials to draw a line, tie line, but that tie line should be passing through the F point. Now that will be done by Thailander. So you're going to assume different values for this one, and every time you get the from extract, raffinate, and then you extend it until you find a line that is going to, when you extend it, will pass it through the feed point, and that line should be extended with this line, and this will represent the delta R minimum. So what we're going to use this, we will, once we do that, we can connect this one, and we can connect this one with this one obtained by trial and error. And then I will say this is my xm that represents the minimum. And I go back to the same equation. We say x minimum is equal to x feed multiplied by feed darb plus x solvent multiplied by S minimum now, divided by S minimum plus the feed. So now this one is obtained from the graph, as you see here. So now this is the tie line. So now let's say, so this is 45, this is your feed, and this is your solvent because it's a pure solvent, as it is stated here in the statement of the problem. Here, with pure solvent. Now you're going to do this by trial and error. This is the tie line. But when you extend this tie line, you see that it is passing through this point. So that will be representing delta R minimum. Now, once I locate this XE1 minimum, I connect it with the XR because this one is fixed. It's 10%. He says the raffinate should contain 10% only. Now, I want to connect this one with, and this one is already there. The crossing is going to represent what? XM minimum. I substitute it here. I can find SM minimum. Now, if you do that, you will find that XM minimum is around 38.18. So it's very close to 40. And therefore, from the equation here, from this equation, so I can say now this, I know this is 0.38. Let's say 1.8 is equal to, the feed contains how much? We said it's 40% and 1,000. So the feed is 1,000 multiplied by 0.5 plus 0 pure solvent multiplied by S minimum divided by S minimum plus the feed, which is 1,000 here. Now, if you solve this equation for S minimum, you will find S minimum to be 178, or let's say 200 or 178.65 kilogram per second. It's not per hour, by the way. Per hour, yes. Now I know this is minimum. What I'll do now, I'll have to find out the number of stages, but now I have to change the flow rate of the S because he's telling me from the statement of the problem, part B, the number of stages required for a solvent trade equal to 1.5 times. So I will work out the problem where this is X actual is equal to 1.2, I think 1.5, sorry, multiplied by S minimum. So now if I say 1.5 multiplied by this 178, 1.65, you will find some number kilograms. You will use this one. Now you will use this one to determine what now? You have to do backward calculation so you can get XM now. So now the XM actual, this is what you have to do. So you say, now you know S minimum is equal to, we obtained it is equal to 178.65 kilogram per hour. Now from this one I can say S actual is equal to 1.5 multiplied by this number 178.63, and so now is actual is going to be what? I go to the calculator. So 1.5 multiplied by 178.63, it's going to be 267.945 kilogram per hour. So now I will use this one to obtain x minimum. Xm actual will be, the feed is 1000 as it is stated here in the statement of the problem, and it contains, so 1000 multiplied by 0.45 plus the solvent is pure, so there's no need to include it here, 0 over 1000 plus 267.945. So if you do that, that will be 450 divided by 1267.945. Now your XM should be, now if I do that, so if I say 450 divided by, sorry, what is that? Yes, sorry. 450 divided by 1267.945, and it's going to be 0.35, almost 10, 0.35. So now I know this one, this point already, and I know the solvent, and I know the feed. All what I have to do is to determine what is the value of XE here. It's not given, but I know now XM. So I go to that, and XM is around this one, XM. I go horizontally. I locate this one, the crossing. So I go at this point, and I extend my line, and I draw a line here that is passing through this one. And then the crossing here will represent E1. Why? Because E1 is at equilibrium with, if you remember, this is your feed, it's going to be at equilibrium with R1. And this is your stage 1 and 2 and so on. And this one B is going to be E2, and this one is going to be R2, and this one is going to be E3, and so on. Now, once we do that, once we specify or locate the E1, what I do now, I draw a line between this one and this F point, and I extend it, and I extend this line, and the crossing here will represent that R. Now it's going to be the actual value. Okay. What I do now, once I know everything, all what I have to do, let me go back to. Now I know E1. I go to the diagram. This is this diagram here that we draw. This diagram from E1. Now E1 is here we see maybe 0.5 something. If you see it, it's around 0.5. Yeah, 0.55. So E1 is 0.55. So X1 EX1 is equal to 0.55. From equilibrium, I can get XR1. Okay, so XR1, I go to the diagram here. This is the extract, so it's 0.55. I go here. So it might be 0.4 something, 0.41 or. Okay. So I go back and 0.41. This one could be the first point here. This is going to be XR1 is equal to 0.41. Now, once I know this one, I connect it to the delta R, and I extend this line to obtain E2. Now, XE2, maybe 0.5. Let's say 0.5. So I go again to the diagram. This one probably 0.41. I go back to 0.5, so I go to the diagram here, 0.5, so it could be 0.39 maybe, just approximation, 0.39. So 0.39, so somewhere here. So I extend it to here, and then I draw another line. That will be my E3, and so on. I continue doing that until I reach to this stage. Okay. Any questions? Now I did probably 3 stages here. Showed you the 3 stages just to help you uh, to start the calculations. Now what I did here using the right triangular, you can do it with equilateral triangular. It doesn't have to be all the time like this one. But the principle is the same. All the time, step one is to locate your feed and solvent points and XRN. And now if you are given the solvent flow rate, you can determine M point by the same equation we use all the time. And you get this M point, you extend the line to get E1 or XE1, which is going to be located exactly on the equilibrium line to the left, to the solvent region. And you connect it to the feed point, and you do a line, draw a straight line, and you connect the solvent with the with the Rn, and you extend that line. The crossing between these two lines will give you delta R. And then once you know delta R, that point is going to be used to draw the other lines. How? We're going to go, I know E1, so I can get XR1. From XR1, I connect it to the delta R and I extend the line to get the E2. Now, how many stages will depend on the equilibrium data you have. Okay? Is that clear, guys? Any questions? Okay, there's one point I want to mention here. Now, I know how to determine the minimum. Now here we did the minimum. Now let's assume someone wants you to determine the maximum. How you determine the maximum? How you determine the maximum? The maximum is going to be in the other side. Now here it is not clear, but the maximum is going to be the one that is going to cross here. This is going to represent XM maximum. Now if you have XM maximum, then this is similar to the one stage calculations. Okay, you go to the other side, the extract layer. Yeah, this is the extract layer. So now once you know xm that represents the maximum, you can use the equation xm is going to be the feed multiplied by x feed plus S maximum. Now here is going to be X solvent if you have any solvent, if you have any solute in your solvent, divided by X maximum plus your feed. So you're going to have only one unknown in this equation, since this one will be located from the graph, and that is going to be the point where the equilibrium line and the feed solvent line crossing. Okay, so if we do zooming here, this is your line, for example, and this is your solvent and feed line. This is your XM that represent the maximum solvent. It's not the XM maximum. Okay, it's the XM minimum, in fact, but will represent the maximum solvent, or you can use it to calculate the maximum amount of solvent that can be used. Okay, guys, any questions? Okay, then thank you very much. Enjoy your time. Today we will have the quiz at 4:30, inshallah. I will post also the last assignment, and the assignment will be on uh, something you have to do using HISIS, inshallah. And hopefully everyone has access to a HISIS. If you don't have access to HISIS, you can arrange with the department to come to the university to do it in one of the labs available. Okay, it's not a big deal, but something that we want you to learn, because one of the skills or learning outcomes you have to acquire in these courses to solve distillation problems, or let's say separation problems, using the process softwares. And basically, this is what you will do in the rest of your life. You're not going to go back to these graphical methods simply because they are not accurate, and basically, not all the not in every case you have two component system. Uh, Most of the time, we will be dealing with multi-component system, and you are looking for some sort of more rigorous methods. And the recent developments in the computer softwares allowed us to implement all the and rigorous methods that usually require lots of calculations and iterations to be done by computer. So now it's easy to be done, so you can get accurate, and it's very quick answer without going back to these drawings. Okay, so thank you very much again, and inshallah see you on Monday next week. Inshallah. Thank you very much, guys.